Now this is a 6-element Yagi for 435 megahertz, completely homebrew. We have, however, gone for the commercial look with the folded dipole and matching transformer section of coax, which I'll explain a bit more later. The main unique feature of this antenna is the attachment arrangement, so that we don't need to drill holes into the boom, and that all the elements are infinitely adjustable laterally. So the attachment method is a single nut, place the element, stabilizing mounting bracket, a 5mm stainless steel stud that's attached with stainless steel hose clamp, so that clamps the stud hard up against the boom, but allows for lateral movement anywhere on the boom. So we've gone for a triangle cut into here so that any diameter element can be fitted. That's fairly universal. The mounting, simply take the element over there, center everything. That allows for a little bit of a adjustment. Now tight. So the folded dipole comes off in the same manner, same mounting bracket. Okay, the matching coax is just a length of 75 ohm coax fed through the folded dipole, connected, sealed, and it's approximately one full wavelength. Now, it's not quite, but it's very close to one wavelength. There is a method for measuring this. I will demonstrate that. But very simple. So with this matching section you will get a fairly close match, and then the final adjustments are by moving the reflector back and forth, which we can see we can do that easily by loosening the hose clamp, and then the first director can also be adjusted. And surprisingly, that will have very little effect on the overall gain of the antenna. The dimensions for the Yagi antenna were acquired from this online Yagi calculator. So pretty straightforward. The frequency is keyed in, so 435 megahertz. The number of elements, which is the reflector, the driven element, and the 4 directors, so 6 elements. The element diameter, which is 10 mil, the boom diameter, which is 20 mil, and show details. And there we have all the dimensions for a Yagi antenna with 6 elements for 435 megahertz. Also indicates the approximate gain, specified as 9.4 dB. Now I use these dimensions as a guide, a starting point. The reflector and the first director, the position will be adjusted to resolve the best SWR, best match. Other than that, it's a fairly good guide. Also, there is some information on the folded dipole. So again, we can key in the frequency of interest of inches or millimeters. That's really the only option you get, and calculate. And based on this drawing here, there's all the dimensions for a folded dipole for 435 megahertz. Alright, I'm going to talk about the folded dipole and the matching transformer section of 75 ohm coax. They're in this instance pretty integrated. Now first off, folded dipole is not the only way that we can feed a Yagi antenna, and feeding the coax through the folded dipole is not the only way to feed a folded dipole. But we've gone for this way to just see what this technique is like. It's also fairly robust and weatherproof, and it's a lot of advantages going for this, but it is a little difficult to construct. So the first consideration is the tube needs to be bent without collapsing the tube, so that the coax can be fed through. The only way I could do that was with a pipe bender. So this is 12mm aluminium tubing. The standard plumbing pipe benders are 12mm or ½ inch. So that worked out alright. It's a fairly large tube for a folded dipole at 435 megahertz. And my first point of confusion was that there's a bit of literature around that says from end to end there's a half wavelength, and that turns out to be not quite the case. You actually have quite a bit of trial and error until I got it right. So the dimensions roughly work out to, this is a full wavelength loop. This is how it should be thought about. It is a fairly thick diameter, so the length is reduced by around somewhere between 5 and 10%. So it's one wavelength minus between 5 and 10%. There's a 10mm gap where the folds meet, so you deduct that as well. So it is a wavelength minus 5 or 10% minus 10mm, and that will give you a folded dipole pretty much where you want it. So I'll demonstrate the pipe bending tool. It's a little bit cumbersome, but the one I had available at the local hardware store was what I had to work with. So once that's completed, the coax is terminated to either side of the folded dipole. We had a rigid sleeve that slid over the top of that to give it some support, and then there's 2 layers of heat shrink shrunk over that. There's also a little bit of silicone around the ends to ensure water tightness. The coaxial cables fed through this grommet here. Behind the grommet there's also been some silicone squeezed in there to reduce water ingress. Depending how the antenna is originally mounted, so if it's vertical, we would probably put a drain hole at the bottom so that any moisture would drain to the bottom. However, in this instance it's mounted up this way. If any moisture gets in through the mounting hole, it'll probably drain out through the same spot. So that's the folded dipole. The 75 ohm matching transformer section, I will demonstrate how that's determined, but is essentially one wavelength down to the termination. That's what it works out to. I will show how I've determined that, and how it pretty much comes out to a full wavelength. Alright, this is not the only way to terminate the coax. Using the exact same formula, one wavelength of transformer section. It can be directly connected here in a box and led away. I've done that. It matches up exactly the same. I have also used a 4:1 coaxial balun and connected at this point, and it matches up the same. So there are multiple ways of connecting the feed line to a folded dipole. And as I say, a folded dipole is not the only type of driven element that we can use on a Yagi antenna. But I think this is a fairly robust construction, and once it gets put up on the tower, I would expect it will not require much maintenance. Okay, this is the method I use to determine the length of the 75 ohm coax transformer section. So we are trying for approximately one wavelength of 75 ohm, and the way I've determined this is I've got the NanoVNA in SWR mode. Got this short length of coax. The SWR has been calculated at the end. We've got a 50 ohm load on here. So if the transformer section is taken out, we essentially have a 1:1 SWR. So in this instance, this is not for 435 megs, this is for between 800 and 1100 megahertz. As I've got a bit of coax made up for roughly that length. So we just connect the transformer section back in. And so essentially where we get a dip, a match, is the length of coax that we need. Now if for argument's sake we were targeting, let's say 1 gigahertz, then the coax just simply needs to be trimmed. Take a small section off. And as you can see, we've gone too far. So just taking that amount off at 1 gigahertz has taken too much off. At 435 it will be not quite as critical, but I guess that underlines trimming small amounts. So this has resulted in us being yeah, 1031 megahertz, so we're 30 megahertz higher than where we needed to be. But essentially that is the technique for determining this. It's reasonably broadband, so not, again, super critical. This would probably be okay for 1 gigahertz even. So yeah, we've gone from approximately 300 mil to 290 mil. And the calculation says that for 1034 megs, the full wavelength is 290 mil. So yeah, that's the technique for determining the transformer section of 75 ohm coax. With the Yagi fully assembled, the folded dipole in position, we're doing a feed line SWR reading, and we're recording pretty much one-to-one SWR at 435.5 megahertz, pretty much the center of the target frequency. So from 434 to about 437, we're at 1.5 to 1. Just take this out a bit further. Let's have a look. 430 megahertz. Not quite high there. So 2.5 to 1, we're at 441 megahertz. To about 432 megahertz. So almost bandwidth of 10 megahertz, which I guess is pretty good. But most importantly, it's centered around 435 megahertz. All right, that's an excellent result. This is the antenna range testing for the Yagi to determine the gain of the Yagi, its ultimate performance. In some ways, perhaps the most important test, because if we don't achieve the desired antenna performance, then every other test is for naught. So the comparison is the Yagi as compared to a standard dipole for the same frequency. I have designed two dipoles. They're identical. They don't need to be, but they are in this instance. The dipoles are cut for 435 megahertz. They have a sleeve balun to suppress common mode currents in the coax to give a nice uniform radiation pattern. It's pretty important. So one antenna is, one of the dipoles is a source to generate the signal. The other one is a reference, it is a receiver. And that will be swapped out for the Yagi and then we'll see the gain difference. So I've done a fair bit of experimentation and research on this, and the separation between the source and the reference antenna and the antenna under test is not super critical, but it does need to be within a range of about 2 to 3 wavelengths. Distances that are significantly greater than 3 wavelengths will introduce inaccuracies due to multipathing of the signal, including ground reflections. So, 3 wavelengths is about the cutoff. At 435 megahertz, 3 wavelengths is about 2 meters separation. The separation of the source antenna and the antenna under test are taken from the dipole to the Yagi driven element and not from the last director of the Yagi. I was a little unsure of that, but apparently that is how it's meant to be done. The antennas need to be at least 1 or 2 wavelengths above the ground. This is to reduce ground reflections that lead to inaccuracies. At 435 megahertz, 2 wavelengths is about 1.5 meters, which is where I've got the antennas set to in terms of height above the ground. Another issue that's worth taking into account, and I have, is that the test should be done in a horizontal polarization. So this reduces ground reflection. Vertical polarization is more sensitive to ground reflections. So everything's set up in horizontal. So the site needs to be as clear as possible from any metallic objects, as far as we can. The gain of the 6-element Yagi can vary on several factors, including design specifications and construction quality. However, as a general rule, we can expect a 6-element Yagi to produce a gain of around 8 to 10 dB above a dipole, or approximately 10 to 12 dBi, that's decibels, over an isotropic antenna. So the next thing is to set up the NanoVNA. So we're going into the So we're in the log mag setting. We're setting that's 0 dB, minus 10, minus 90, which is too much, so we'll just set the scale to to 2 dB per increment. So ideally we'll see the Yagi sit about halfway in the display. I'm going to set the frequency range 435 megahertz to 436 megahertz. Now we need to calibrate. Now we've got the 2 dipoles set now, so this is going to set our baseline. Reset, calibrate, through, done. So our increments are 2 dB. We're 435 to 436 megahertz in the frequency range we're looking at, and the calibration has set the baseline to 0 dB. So I'm now going to swap the reference dipole with the 6-element Yagi. Okay, the results we're showing is approximately 8.6 dB of gain over the dipole, which is in the range of what we'd expect for a 6-element Yagi. Now, the other common reference for antenna gain for Yagis or any antenna is in gain as compared to an isotropic antenna, commonly referred to as dBi. The gain of a nominal dipole is about 2.1 dB over the theoretical isotropic antenna, so we would add 2.1, that puts us up around about 10.7 dBi, which is about the range we would probably expect for this sort of antenna. So that's about the results I would expect to see, and so I'm quite happy with that.